When a user makes a click on a web page, that localized action immediately scales out into a complex engineering pipeline. The core objective of modern full-stack development is ensuring that this local code logic safely and predictably transits into a live global production environment. This transit requires managing three distinct layers of state: the user's browser, the developer's local machine, and the global production server. To understand how this architecture actually operates, we have to trace the lifecycle of a single interactive feature across all three of these environments. Because an application's front-end interface can only successfully handle millions of users if it is supported by a rigorous, automated back-end infrastructure. This diagram shows the document object model, a hierarchical tree representing the web page. Every element on the screen corresponds to an exact node, like this specific button. To make that node interactive, JavaScript uses an architectural tool called an event listener. It actively intercepts asynchronous user inputs, like a mouse click or a keystroke, directed specifically at that target. Once triggered, the listener executes a localized function that dynamically mutates the DOM. It updates properties like text or background color instantly, bypassing the need for a slow, resource-heavy refresh from the server. Within these functions, developers capture the action using the E, or event, argument. This argument acts as a highly specific data payload. It contains the precise coordinates, context, and parameters of the user's localized action. One of the primary systems engineering use cases for capturing these localized input events is live form validation. By validating the format of an email address locally through an event listener, the front-end instantly rejects malformed data before it can trigger a costly query to the back-end database. Catching these formatting errors exactly as they happen preserves the user experience by providing immediate feedback. Client-side events efficiently handle immediate UI interactions. However, they create a massive secondary problem. Engineering teams now have to safely write, track, and update thousands of lines of precise JavaScript logic over months of active development. This pushes the narrative away from the user's browser and directly into the developer's local command line interface. The primary bottleneck of local software development is safely tracking ongoing code mutations without constantly duplicating entire project directories. Historically, developers relied on manual versioning, creating endless folders named V1, V2, and V3 Final. At an enterprise scale, tracking exact logic changes across thousands of files this way collapses into complete chaos. To solve this local tracking bottleneck, Linus Torvalds, the creator of the Linux operating system, architected a localized version control system called Git. This graph represents Git's core engineering concept. Instead of saving duplicate files, it tracks the delta, the specific mathematical additions and subtractions applied to the code. Tracking these deltas generates a precise, easily navigable historical state on the local machine. If a major error occurs, developers can instantly reverse the timeline to a clean, known good prior state. Because an exact prior state is mathematically recoverable, developers gain the psychological safety required to experiment and break things locally. Git successfully manages the local historical timeline for a single user, yet it inherently lacks the ability to natively synchronize overlapping work from hundreds of developers distributed around the globe. Zooming out to a network topology perspective, we encounter multiple isolated developers, all attempting to work on the exact same project simultaneously. This reveals a common industry misconception. Git is the local versioning engine running on your machine, whereas GitHub is the centralized cloud hosting infrastructure. This network topology map illustrates the necessity of that cloud platform. It enables multi-node collaboration, allowing separate local machines to synchronize their distinct timelines via continuous push and pull mechanisms. To prevent code collisions between these simultaneous developers, this centralized hub relies on a branching tree diagram strategy. Feature branches strictly isolate the writing of new code, ensuring ongoing experiments do not disrupt the stable production branch. Before any of this isolated work can join the main line, a repository maintainer acts as a gatekeeper, manually reviewing the new logic and authorizing the merge. These access control models differ by organization. Open-source repositories rely on public, community-driven review, while closed-source repositories lock this process down for private corporate intellectual property. GitHub resolves the logistical nightmare of global collaboration, but relying entirely on human code review remains statistically insufficient to prevent every single bug from merging into a live product. To protect the live production server from human error, engineering teams deploy continuous integration and continuous deployment pipelines, automated algorithmic gatekeepers. Manual quality assurance testing suffers from a severe structural vulnerability. Human testers physically cannot execute thousands of distinct checks effectively during massive daily deployment cycles. This diagram shows the first automated CI/CD gate, the testing stage. Here, automation scripts written in languages like Python or Java programmatically hunt for logical errors faster than any human could. Once passed, the code packet moves to the second sequential gate, the build stage, often using tools like npm build. This stage is strictly required to convert raw, human-readable development logic into optimized, machine-ready files suitable for deployment. Finally, the artifact enters the security stage, where tools like SonarCube perform a sweeping structural scan to identify deep vulnerabilities. These deployment pipelines operate on strict deterministic logic. Failure at any single point is absolute. If even one automated test fails, the entire pipeline immediately halts, completely blocking the buggy code from contaminating the main production branch. CI/CD shifts the burden of consistency from manual oversight to automated verification. This ensures every deployment meets a predefined set of technical benchmarks, reducing the risk of a single error disrupting the live environment. Engineering a modern web application involves managing the safe passage of logic across multiple, diverse environments. First, JavaScript governs the localized, event-driven user interaction layer directly inside the browser. Second, Git mathematically maps a precise versioning timeline on the developer's local hardware. Third, GitHub orchestrates the distributed topology, safely syncing parallel branches of work from a global team. Finally, CI/CD algorithms provide the final deterministic guarantee, protecting the integrity of the live deployment. Mastering this automated infrastructure is what enables an engineer to manage the lifecycle of a feature from the first